Mount Berlin is a glacier-covered volcano in Marie-Byrd Land, Antarctica, 100 kilometers, 62 miles, from the Amundsen Sea. It is a roughly 20-kilometer wide, 12-mile, mountain with parasitic vents that consists of two coalesced volcanoes, Berlin proper with the 2-kilometer wide, 1.2-mile, Berlin crater and Mirim Peak with a 2.5 by 1 kilometer wide, 1.55 miles by 0.62 miles, crater, 3.5 kilometers, 2.2 miles, away from Berlin. The summit of the volcano is 3,478 meters, 11,411 feet, above sea level. It has a volume of 200 cubic kilometers, 48 cubic miles, and rises from the West Antarctic ice sheet. It is part of the Marie-Byrd Land volcanic province. Trachyte is the dominant volcanic rock and occurs in the form of lava flows and pyroclastic rocks. View of Mount Berlin from the surrounding ice sheet. Marie-Byrd Land, Antarctica. Regarding Mount Berlin, and regarding highest point, its elevation is 3,478 meters, 11,411 feet. Its coordinates are 76 degrees south 136 degrees west. Regarding geography, and regarding geology, its last eruption was 8,350 plus minus 5,300 BCE. The volcano began erupting during the Pliocene and was active into the late Pleistocene and the Holocene. Several tephra layers encountered in ice cores all over Antarctica, but in particular at Mount Moulton, have been linked to Mount Berlin, which is the most important source of such tephras in the region. The tephra layers were formed by explosive eruptions that generated high eruption columns. Presently, fumarolic activity occurs at Mount Berlin and forms ice towers from freezing steam. Mount Berlin lies in Marie-Byrd Land, West Antarctica, 100 kilometers, 62 miles, inland from the Hobbs coast of the Amundsen Sea. The volcano was studied during field trips in December 1940, November 1967, November to December 1977 and 1994 to 1995. It is named after Leonard M. Berlin, who led the 1940 research visit to the mountain. Topographical map of Mount Berlin. Mount Berlin reaches a height of 3,478 meters, 11,411 feet, above sea level, making it the highest volcano in the flood range. It is the western end of the range. Wells Saddle separates it from Mount Moulton volcano farther east. Mount Berlin's peak is 2.1 kilometers, 1.3 miles, above the highest local elevation of the West Antarctic ice sheet. The summit crater, Berlin crater, is 2 kilometers, 1.2 miles, wide and has sharply defined, ice-crowned edges. The highest point of the volcano is on the southeastern margin. Mount Berlin consists of two overlapping edifices, Mount Berlin proper and Mirim Peak, 3.5 kilometers, 2.2 miles, west-northwest. Mirim Peak is about 3,000 meters, 9,800 feet, high and has a 2.5 by 1 kilometer wide, 1.55 miles by 0.62 miles, crater at its summit. These craters are aligned east-west, like other flood range calders. Mount Berlin has variously been described as a composite volcano, shield volcano or stratovolcano with a volume of about 200 cubic kilometers, 48 cubic miles. The entire combined edifice has a length of about 20 kilometers, 12 miles. Its slopes have inclinations of about 12 to 13 degrees. The volcano is covered by glaciers, resulting in only a few rocky outcrops being visible on the mountain. Despite this, the volcano is considered to be well exposed in comparison to other volcanoes in the region. Monogenetic volcanoes on the northern flank of Mount Berlin have generated two outcrops of mafic lava and scoria, one of which is found at Mefford Knoll on a linear vent. On the southeastern flank, a Fiamme-rich ignimbrite crops out and is correlated to a flank vent on the northeastern flank. A ridge extends northwestward from Mirim Peak, At its foot is Brandenburger Bluff, a 300-meter-high, 980 feet, outcrop of lava and tuff. This structure formed phreatomagmatically. It was formerly interpreted as a subglacial hyaloclastite. Other topographical locations on Mount Berlin are Fields Peak on the northern flank, Kraut Rocks at the west-southwestern foot, Waltz Cliff on the northeastern flank and Wedemeyer Rocks at the southern foot. The existence of tuayas has been reported from Mount Berlin. According to a 1972 report, tephra overlays ice at some sites. Non-volcanic features include incipient cirques on the northern and western side. The Marie-Byrd-Land volcanic province features 18 central volcanoes and accompanying parasitic vents, which form islands off the coast or nunataks in the ice. Many of these volcanoes form distinct volcanic chains, such as the Executive Committee Range, where volcanic activity has shifted westward at a rate of about 1 centimeter per year, 0.4 inches per year. Such a movement is also apparent in the Flood Range, where activity migrated from Mount Moulton to Mount Berlin. This movement appears to reflect the propagation of crustal fractures, as plate motion is extremely slow in the region. Volcanic activity appears to take place in 3 phases: an early mafic phase, often followed by a second felsic phase. End-stage volcanism occurs in the form of small cone-forming eruptions. Ignimbrites are rare in Marie-Byrd-Land. The outcrop on the southeastern flank of Mount Berlin is an uncommon exception. Activity in the Marie-Byrd-Land volcanic province began during the Middle Miocene and continued into the later Quaternary. Argon dating yielded ages as young as 8,200 years. 4 volcanoes in the Marie-Byrd-Land volcanic province, Mount Berlin, Mount Sippel, Mount Acke and Mount Wesk, were classified as possibly or potentially active in the 1990 Antarctic Research Series by Lemagerier et al., and active subglacial volcanoes have been identified on the basis of aerophysical surveys. The volcanic province is related to the West Antarctic Rift, which is interpreted as a rift or as a plate boundary. The West Antarctic Rift has been volcanically and tectonically active over the past 30 to 25 million years. The basement crops out near the coast and consists of Paleozoic rocks with intruded Cretaceous and Devonian granites which were flattened by erosion, leaving a Cretaceous erosion surface on which volcanoes rest. The volcanic activity at Mount Berlin may ultimately relate to the presence of a mantle plume that is impinging onto the crust in Marie-Byrd-Land. Two pyroclastic fallout deposits crop out in the crater rim, reaching thicknesses of 150 meters, 490 feet. Other outcrops of fallout deposits occur at Mirim Peak. The Mount Berlin deposits reach thicknesses of more than 70 meters, 230 feet, close to the crater, diminishing to 1 meter, 3 feet, at Mirim Peak. They were formed by pyroclastic fallout during eruptions, which mantled the topography. As eruption characteristics changed, these processes generated distinct deposits. Tuff deposits containing lapilli and volcanic ash-rich pyroclastic deposits in the crater rim were erupted during hydromagmatic events. Some lava flows feature levee-like forms at their margins. In the past, certain fallout deposits in the crater rim were thought to be lava flows. Hyalotuff, obsidian and pumice have been recovered from Mount Berlin. Both welded and unwelded pyroclastic and tuffaceous breccias are present. They consist of lava bombs, lithic rocks, obsidian fragments and pumice. Hyaloclastite occurs around the base of Mount Berlin. Most volcanic rocks of Mount Berlin define a trachyte suite, which features both commendite and pantellerite. Phenolite is less common. Mafic rocks have been reported from flank vents, basanite and hawaiite from Mefford Knoll, benmorite from the southeastern flank at Wedemeyer Rocks, phenotephrite from Brandenburger Bluff, and mugierite without any particular locality. Phenocrysts make up only a small portion of the volume and consist mostly of alkali feldspar, with subordinate apatite, phyllite, head and bajite and opaque minerals. Benmorite has more phenocrysts, which include anorthoclase, magnetite, olivine, plagioclase,
pyroxene and titanorgite. Ground mass include basanite, mafic rocks, trashite and trachyphenolite. Xenoliths are also recorded. The magma erupted from Mount Bilin appears to have originated in the form of discrete small batches rather than in one large magma chamber. The composition of volcanic rocks varied between eruptions and probably also during different phases of the same eruption. Phenolite was erupted early during volcanic evolution and followed by trashite during the Quaternary. A long-term trend in iron and sulfur of the tephras may indicate a tendency towards more primitive magma compositions. Mount Bilin was active from the Pliocene into the Holocene. The oldest parts are found at Wedemeyer Rocks and Brandenburger Bluff and are 2.7 million years old. Activity then took place at Murrumbidgee between 571,000 and 141,000 years ago. During this phase, eruptions also occurred on the flanks of Mount Bilin. After 25,500 years ago, activity shifted to Mount Bilin proper and the volcano grew by more than 400 meters, 1,300 feet. Over time, volcanic activity on Mount Bilin has moved in a south-southeast direction. Eruptions of Bilin include both effusive eruptions, that emplaced cinder cones and lava flows, and intense explosive eruptions, Plinian eruptions, which generated eruption columns up to 40 kilometers, 25 miles, high. Such eruptions would have injected tephra into the stratosphere and deposited it across the southern Pacific Ocean and the West Antarctic ice sheet. The patterns of tephra deposition indicate that westerly winds transported tephra from Mount Bilin over Antarctica. During the last 100,000 years, Mount Bilin has been more active than Mount Takei, the other major source of tephra in the West Antarctic, but activity at Bilin was episodic rather than steady. The volcano underwent a surge in activity between 35,000 and 40,000 and 18,000 and 20,000 years ago. Despite their size, the eruptions at Mount Bilin did not significantly impact the climate. The eruption history of Mount Bilin is recorded in outcrops on the volcano, in a blue ice area on Mount Moulton, 30 kilometers, 19 miles, away, at Mount Wesk, in ice cores and in marine sediment cores from the Southern Ocean. Several tephra layers found in ice cores all across Antarctica have been attributed to West Antarctic volcanoes and in particular to Mount Bilin. Tephras deposited by this volcano have been used to date ice cores, establishing that ice at Mount Moulton is at least 492,000 years old and thus the oldest ice of West Antarctica. Dusty layers in ice cores have also been linked to Mount Bilin and other volcanoes in Antarctica. The location of some places mentioned in the text, excluding Mount Moulton which is close to Mount Bilin: Amundsen Sea, Billingshausen Sea, Sippel Dome, Mount Bilin, Taylor's Dome, Mount Erebus, Dome C, Vostok Station, and Dome F. Among eruptions recorded at Mount Bilin are 492,400 plus minus 9,700 years ago, recorded at Mount Moulton. 19, a 443,000 plus minus 52,000 years old lava at Murrumbidgee may correlate to this eruption. Tephras in the Vostok Station ice cores of East Antarctica deposited 406,000 years ago may have came from Mount Bilin. Cinder cones at Mefford Knoll have been dated to be 211,000 plus minus 18,000 years old. Potassium argon dating there and at Kraut Rocks has yielded ages of 630,000 plus minus 30,000 and 620,000 plus minus 50,000 years, respectively. 141,600 plus minus 7,500 years ago, recorded at Mount Moulton. It may correspond to a 141,400 plus minus 5,400 years old deposit at Murrumbidgee. A 141,700-year-old tephra layer at Vostok has been related to this Mount Moulton tephra. The marine tephra B, which has been identified in marine sediment cores and the Dome Fuji ice core, was erupted by Mount Billin 130,700 ± 1,800 years ago. It is used as a stratigraphic marker for the transition between marine isotope stages 6 and 5. 118,700 ± 2,500 years ago, recorded at Mount Moulton and potentially also at Taylor's Dome. Correlated deposits at Sipple Ice Dome indicate that this eruption was intense and deposited tephra over large areas. 106,300 ± 2,400 years ago, recorded at Mount Moulton. 92,500 ± 2,000 and 92,200 ± 900 years ago, as dated by argon dating of its deposits around Mount Berlin. A tephra layer in Dome C and Dome Fuji ice cores recovered during European project for ice coring in Antarctica and dated to be 89,000 to 87,000 years old has been attributed to this eruption on the basis of its composition. The nature of the trachytic tephra layer indicates that it was produced during an intense, multiphase eruption which may have led to compositional differences between deposits emplaced close and these emplaced far from the volcano. Deposits from this eruption have also been found in the Amundsen Sea, the Bellingshausen Sea, at a Vostok ice core and in marine sediments of the continental margin of West Antarctica. Tephra A, a 28,500-year-old tephra layer at Mount Erebus and into ice cores of the West Antarctic ice sheet. 27,300 ± 2,300 years ago, recorded at Mount Moulton. Ages of 25,500 ± 2,000 years ago have been obtained from two lower welded pyroclastic units that crop out within Mount Berlin crater. Unwelded obsidian fallout units that crop out in Mount Berlin crater have been dated to be 18,200 ± 5,800 years old. 14,500 ± 3,800 years ago, recorded at Mount Moulton. A lava flow and tephra layers found both close to and away from Mount Berlin appear to have been produced during an extended eruption about 10,500 ± 2,500 years ago. 9,718 BP, as dated in the Sipple Dome ice core. A lava flow on Mount Berlin and tephras at Mount Moulton have a similar composition though no exact match has been found. Several tephra layers between 18,100 and 55,400 years old, found in Sipple Dome ice cores, resemble those of Mount Berlin, as do tephras emplaced 9,346 and 2,067 BCE, interval 3.0 years, in the Sipple Dome ice core. The marine tephra B and tephra C layers may also come from Mount Berlin, but statistical methods have not supported such a relationship, at least for tephra B. A 694 ± before present tephra layer found in the Taldus ice core in East Antarctica may come from Mount Berlin or from Mount Melbourne and may have been erupted at the same time as an eruption of the Pleiades. The date of the last eruption of Mount Berlin is unclear, but the Global Volcanism Program gives 10,300 ± 5,300 BP as the date of the last known eruption. Because of its Holocene activity, the volcano is considered active and several volcano-tectonic earthquakes have been recorded on Mount Berlin. Mount Berlin is geothermally active, the only volcano in Marie Byrd Land with such activity. Steaming ice towers are found on the western and northern rim of Berlin crater. Their existence was first reported in 1968. Ice towers form when fumarole exhalations freeze in the cold Antarctic atmosphere and are a characteristic trait of Antarctic volcanoes. ASTER satellite imaging has not detected these fumaroles, presumably because they are hidden within the ice towers. A more than 70-meter long, 230-foot, ice cave begins at one of these ice towers. Temperatures of over 12 degrees Celsius, 54 degrees Fahrenheit, have been recorded on the cave floor. These geothermal environments may host geothermal habitats similar to those in Victorialand and at Deception Island, but Mount Berlin is remote and has never been studied in this regard. It has been evaluated for the potential to obtain geothermal power. Being isolated and extensively covered with ice, these volcanoes are unlikely to have any significant economic value as geothermal resources.